On June 11, 2025, the European Space Agency released a set of images that scientists had been chasing for more than 60 years. And the moment they went public, solar physicists everywhere started using the same word, historic, a word that gets thrown around a lot in science journalism, but rarely actually earns it the way this discovery did. The European Space Agency's Director of Science, Professor Carol Mundell, stood up and said it plainly. Today, we reveal humankind's first ever views of the sun's pole, not an artist's impression, not a computer simulation built from decades of guesswork, actual photographs taken by an actual spacecraft called Solar Orbiter, showing our own star's south pole for the very first time in the entire history of human civilization. Every single image of the sun you have ever seen in your life, every photograph in every textbook, every sunrise, every eclipse, has come from exactly the same angle, staring straight at the sun's equator, face on, like looking at someone directly in the eyes and never once seeing the top of their head. That's not a coincidence or a limitation of camera technology. It's basic orbital mechanics, and it means that for the entire span of human history, roughly a third of our own star has remained completely, totally invisible to us, until March of 2025. On March 16th and 17th, Solar Orbiter tilted itself out of the plane every other spacecraft and planet has ever occupied, and looked down at the sun's south pole from an angle no human instrument had ever achieved. And what it found, waiting there, wasn't calm, orderly, and predictable. It was chaos, a magnetic field so tangled and mixed up that scientists are still trying to fully make sense of it months later. And here's why this should genuinely grab your attention right now. The chaos at the pole isn't just a curiosity, it's the missing piece behind why solar storms strong enough to fry satellites, black out power grids, and cost the global economy trillions of dollars have remained frustratingly unpredictable for generations, and we may have finally found the vantage point that changes that. It's also a genuinely humbling reminder of how much we've simply assumed about our own star without ever actually confirming it. In much the same way, ancient astronomers once assumed the entire universe revolved around us, because that's simply what it looked like from where they were standing. So let's break down exactly what Solar Orbiter saw, why nobody had ever seen it before, and what it actually means for the safety of everything you rely on every single day. That comparison to ancient astronomy isn't just a throwaway line either. For most of recorded human history, going back through ancient Greece and well into the Middle Ages, the dominant scientific view held that the Earth sat motionless at the center of everything, with the sun, moon, and every visible star quietly circling around us. It was called the geocentric model, and it made a certain intuitive sense because, from the ground, everything genuinely does appear to move around the observer. It wasn't until the 16th century that this model was seriously overturned in favor of a sun-centered picture of the solar system, and even that heliocentric model, as accurate as it became, still quietly carried forward an old assumption that scientists were somehow seeing the sun completely simply because they could see it every single day. In reality, every single observation made under that heliocentric model for the following 5 centuries still came from the exact same narrow equatorial slice of the sun that ancient astronomers had access to. We corrected where the Earth sat in space long before we corrected the angle from which we were actually looking at our own star. Solar Orbiter's polar images represent the next real correction in that same multi-century story, closing a gap in our perspective that had quietly persisted for the entire span of modern astronomy. To understand why this moment took 60 years to arrive, you first have to understand something genuinely strange about how we've always watched the sun. Every planet in our solar system, Earth included, orbits the sun along roughly the same flat plane, something astronomers call the ecliptic. Every single spacecraft humanity has ever launched toward the sun, going all the way back to the earliest solar observatories, has traveled along that same flat plane too, because it's dramatically more fuel efficient than fighting your way out of it. The problem is that if every observer sits on that same flat disk, every observer only ever sees the sun from the side, staring straight at its equator. Nobody has ever been positioned above or below it to actually look down at the poles directly, not because scientists didn't want to, but because getting a spacecraft to tilt itself out of that plane requires an enormous, expensive fight against the basic physics of orbital motion. There was exactly one earlier exception. A joint ESA and NASA mission called Ulysses did fly over the sun's north and south poles back in 1994 and 1995, but Ulysses carried no cameras at all, only instruments that measured particles and magnetic fields as it passed by roughly 200 million kilometers away. It told scientists something was happening up there, but it never let anyone actually see it. That's the 60-year gap Solar Orbiter was built to finally close. Solar Orbiter itself launched on February 10th, 2020, a joint mission between the European Space Agency and NASA, and it had been monitoring the sun from the familiar equatorial viewpoint since November of 2021. But the mission's real purpose was always about reaching the poles, And to do that, engineers used a series of carefully choreographed gravity-assisted flybys of Venus to gradually bend the spacecraft's orbit out of the ecliptic plane. Each flyby added a little more tilt. By February of 2025, Solar Orbiter had climbed to an inclination of 17 degrees below the solar equator, more than double what any previous sun-observing mission had ever achieved. And crucially, it was doing this while flying dramatically closer to the Sun than Ulysses ever had, at a distance of roughly 40 million miles compared to Ulysses' 125 million miles. That combination, real proximity plus real imaging instruments plus a genuinely novel viewing angle, is exactly what made March 2025 the moment everything changed. On March 16th and 17th, from that 15 to 17 degree angle below the equator, Solar Orbiter pointed 3 of its most important scientific instruments directly at the Sun's south pole and captured data unlike anything ever recorded. The first instrument, called the Polarimetric and Helioseismic Imager, or PHI, captured the Sun in ordinary visible light, showing the actual surface, known as the photosphere, and simultaneously mapped the direction of the magnetic field along the spacecraft's line of sight. Now, the second instrument, the Extreme Ultraviolet Imager, or EUI, captured the Sun in ultraviolet wavelengths, revealing the outer atmosphere, the corona, where temperatures reach well over 1,000,000 degrees. The third instrument, called SPICE, mapped where different charged particles sit within that outer atmosphere, effectively building a temperature and composition map of the region layer by layer. Individually, each instrument gave scientists a new kind of data. Combined together, they gave humanity its very first genuinely complete picture of what exists at the top of our own star. And what that combined picture revealed was almost immediately surprising. Under normal quiet conditions, a star's magnetic poles behave a lot like a simple bar magnet, one clear dominant polarity at each end, positive at one pole, negative at the other, clean and orderly. That is not remotely what Solar Orbiter found. Instead, the PHI instrument showed that the Sun's south pole is currently, in the words of ESA's own release, a mess, patches of both positive and negative magnetic polarity scattered right up to the pole itself, with no single dominant direction anywhere in sight. There was a second surprise buried inside the same dataset too. Follow-up analysis of Solar Orbiter's south pole observations found that the Sun's magnetic field appears to be carried toward the pole considerably faster than existing models had predicted. A detail that sounds small on paper but actually forces solar physicists to reconsider some of the basic assumptions baked into how they simulate the dynamo process. When the fundamental speed at which magnetic material migrates toward the pole turns out to be wrong, every downstream prediction about timing, intensity, and duration of the solar cycle built on top of that assumption needs to be revisited too. Solar Orbiter's mission manager, Annick de Groof, explained that during a solar minimum, you'd expect a clean North Pole and a clean South Pole, each holding its own distinct polarity. But right now, during this period of maximum solar activity, the star is in what she called magnetic chaos, with no dominant polarity found at either pole at all. This messy magnetic signature isn't a malfunction or a fluke. It's actually a signature of something specific happening to the entire star, because this exact kind of tangled polar mess only appears for a short window during each roughly 11-year solar cycle, right at the moment the Sun's global magnetic field is in the middle of completely flipping itself inside out. That flip, called the solar magnetic reversal, is one of the strangest and least understood behaviors of our entire star. Roughly every 11 years, the Sun's north and south magnetic poles trade places. North becomes south and south becomes north, and this reversal happens to coincide almost exactly with the peak of the Sun's overall activity, a period called solar maximum, when sunspots, solar flares, and coronal mass ejections all become dramatically more frequent and more powerful. Scientists have understood the broad outline of this cycle for well over a century simply by counting sunspots on the visible face of the Sun, but the actual mechanism driving it, called the solar dynamo, has remained stubbornly mysterious because nobody could ever directly watch what was happening at the poles themselves while the reversal was actually underway. Think of it a little like how an ordinary electromagnet works. Run electric current through a coiled wire wrapped around a nail, and that nail becomes magnetized. The Sun runs on a version of that same basic principle at an almost unimaginable scale. A colossal ball of hot, ionized, electrically charged gas constantly churning and flowing inside its core. And wherever you have that kind of moving electric current, you generate a magnetic field alongside it. That churning process is the dynamo, and it's ultimately responsible for every sunspot, every flare, and every violent eruption the Sun ever produces. But the fine details of exactly how it builds up, weakens, and eventually flips at the poles had never actually been observed directly until this year. This is precisely where the timing of Solar Orbiter's arrival becomes almost unbelievably lucky. Solar Orbiter isn't the only spacecraft that had to get uncomfortably close to the sun to answer questions ground-based telescopes simply couldn't touch. Back in 2021, NASA's Parker Solar Probe became the first spacecraft in history to physically fly through the sun's outer atmosphere, the corona, effectively touching the surface of a star for the first time ever. That mission revealed something scientists had puzzled over for years. Strange magnetic zigzag structures rippling through the solar wind called switchbacks, whose origin remained a mystery until Parker Solar Probe flew close enough to trace them directly back to the sun's surface itself. Researchers discovered that the sun's superheated atmosphere is bound together by magnetic forces and gravity right up until it reaches a boundary called the Alfvén critical surface, the point where the sun's gravity and magnetic field can no longer hold onto the material, and beyond which that material becomes the solar wind, permanently severing its connection to the star and streaming outward toward Earth and beyond. Parker's solar probe discovered that boundary isn't a smooth, even sphere the way scientists had long assumed. It's wrinkled, with valleys and spikes, and at one point the probe even passed through a massive structure called a pseudo-streamer, a region so much calmer than the surrounding solar wind that scientists described it as flying into the eye of a storm. Solar Orbiter and Parker. Solar Probe are essentially two halves of the same overarching mission, one flying close enough to physically sample what the sun is made of, the other tilting far enough out of the ecliptic to finally see the parts of the sun no one had ever laid eyes on, and together they represent the most ambitious, coordinated assault on the sun's remaining mysteries that humanity has ever attempted. Professor Sami Solanki, who leads the PHI instrument team, pointed out that Solar Orbiter reached these high latitudes at precisely the right moment in the solar cycle to watch the entire process unfold from a genuinely unique vantage point that no previous mission had ever occupied. Right now, the sun sits near solar maximum, which means the magnetic mess Solar Orbiter photographed is expected to gradually resolve itself over the next 5 to 6 years as the star settles back toward its next solar minimum. The calm, orderly phase, where the poles should each display one clean, dominant polarity again. For the first time ever, scientists now have direct photographic and magnetic evidence of the starting conditions for that entire multi-year process, rather than having to infer what's happening at the poles indirectly from measurements taken at the sun's equator, millions of miles away from where the actual action is occurring. It's worth pausing here to appreciate just how significant that gap in understanding actually was before this year. For generations, every prediction about solar activity, when the next solar maximum would peak, how intense a given cycle would be, when exactly the poles would flip, was built entirely on models extrapolated from equatorial observations and centuries of sunspot counting. Scientists knew the broad rhythm existed, but they couldn't reliably say when a specific reversal would complete, or how violent a given cycle's peak would actually get, because the region where the process visibly plays out had simply never been photographed. That uncertainty has real consequences, because the same magnetic chaos driving the pole reversal is directly connected to the sunspots, flares, and eruptions capable of reaching all the way to Earth and beyond. When a colossal magnetic filament briefly broke away from the sun's surface in February of 2023, forming a strange vortex that appeared to circle the sun's north pole at roughly 60 miles per second for about 8 hours, astronomers were genuinely baffled. One veteran solar scientist who had studied the sun's cycles for decades said he had never seen anything quite like it. Without a direct view of the poles, events like that stayed mysterious anomalies. With Solar Orbiter's new vantage point, scientists finally have a real chance at understanding what's actually happening in that region when something that strange occurs again. And the stakes here go well beyond simple scientific curiosity, because the sun's activity has a direct, sometimes dramatic impact on modern life back here on Earth. Coronal mass ejections, massive clouds of charged plasma the sun periodically hurls into space, and solar flares, sudden bursts of radiation released when the sun's tangled magnetic field lines snap and reconnect, are both far more frequent and far more powerful during solar maximum, exactly the period we're in right now. In late May of 2025, a geomagnetic storm rated G3, meaning strong, struck Earth after a stream of high-speed solar wind poured out of a coronal hole, and it produced auroras visible as far south as Iowa and Oregon, with agencies warning of possible GPS and shortwave radio disruptions, though no serious issues were ultimately reported. Just days later, on June 1st and 2nd, an even stronger G4 class storm hit, one level below the most severe classification that exists, and it painted glowing green and pink skies across the northern United States and as far south as California and New Mexico, the kind of sight you'd normally have to travel to the Arctic Circle to witness, with astronauts aboard the International Space Station capturing some of the view from orbit while airlines received radiation warnings and adjusted flight paths as a precaution. Mid-June brought a G2 storm, and then, on June 17th and 19th, the sun fired off two powerful solar flares back-to-back, the second of which briefly knocked out radio communications across parts of the United States. None of these individual events caused a catastrophe, but strung together across a matter of weeks. They painted a clear picture of a star ramping up toward peak activity right on schedule, exactly the kind of behavior scientists hope solar orbiters' new polar data can eventually help them predict with far more precision and far more advanced warning. The financial stakes attached to getting that prediction right are genuinely enormous. A powerful geomagnetic storm doesn't hurt people directly, you won't get sunburned through your roof or feel a physical jolt from a solar flare, but it absolutely can hurt the invisible infrastructure holding modern civilization together. When a magnetic disturbance reaches Earth, it can induce electrical currents in the ground that creep into long power lines, and if those currents get strong enough, they can overload transformers, damage electrical systems, and knock out entire regional power grids. Exactly what happened in Quebec in 1989 when a solar storm blacked out the entire province in roughly 90 seconds. Modern life has only become more exposed to this risk since then, not less, given how dependent everything from banking to navigation to communication has become on satellite networks that didn't exist decades ago, with tens of thousands of satellites now in orbit, compared to a mere handful during earlier solar cycles. Researchers have estimated that a single storm on the scale of the legendary 1859 Carrington event, the most powerful geomagnetic storm ever recorded, could cause somewhere between $0.6 and $2.6 trillion in damage inside the United States alone if it struck today, and events of that exact magnitude are estimated to occur roughly once every 500 years, meaning the odds on any given day are low, but the exposure if it happens is staggering. During the original Carrington event, currents surging through telegraph lines around the world sparked fires and knocked out communications entirely. And auroras normally confined to polar latitudes were spotted as far south as Cuba and Honolulu, with witnesses in some regions convinced they were watching the end of the world, while others got out of bed thinking dawn had already broken. Today we understand that kind of dramatic aurora sighting at unusually low latitudes as simply one of the expected effects of the sun's magnetic activity ramping toward its peak, but a repeat of an event that powerful, aimed squarely at a civilization now blanketed in satellites, undersea data cables, and interconnected power grids, would look nothing like a 19th century telegraph outage. This is precisely why ESA and NASA aren't stopping at this one set of images. Solar Orbiter's current 17-degree tilt is only the opening chapter of what mission scientists have started calling a stairway to heaven, a deliberate, staged climb toward ever steeper viewing angles over the coming years. Another close flyby of Venus, scheduled for December 24th, 2026, will push the spacecraft's inclination up to 24 degrees, and by June of 2029, a final adjustment will carry it all the way to 33 degrees below the solar equator, giving scientists their clearest, most complete view yet of both poles working in tandem. Solar Orbiter had already imaged the sun's north pole as well, captured during a separate pass in late April of 2025, though that data took considerably longer to fully transmit back and analyze compared to the south pole images. Mission scientists have been careful to stress that what's already been released is genuinely only the beginning, with the richest scientific findings still waiting inside data that hasn't even been fully processed yet. Beyond Solar Orbiter itself, the European Space Agency is also developing a dedicated new spacecraft called Vigil, specifically designed to sit at a vantage point that will significantly extend how much advance warning Earth gets before a hazardous solar storm actually arrives, essentially building an early warning system informed directly by exactly the kind of polar data Solar Orbiter is now providing. Current space weather forecasting already relies on a constant stream of monitoring from agencies like NASA and NOAA, who track solar activity around the clock and typically manage to give advance warning ranging anywhere from several hours to a couple of days before a major storm actually reaches Earth, enough time in many cases for grid operators to take vulnerable transformers offline before real damage occurs. Vigil is meant to push that warning window further out and make it more reliable, and the polar magnetic data Solar Orbiter is now collecting is exactly the kind of missing input that current forecasting models have never had access to before. What makes all of this genuinely remarkable when you step back and think about it is just how basic the underlying limitation actually was for so long. It wasn't a lack of curiosity or a lack of clever engineering ideas. It was simply the raw physics of orbital motion keeping every human eye and every human camera locked onto the exact same flat viewing angle for the entire span of recorded history. Every civilization that ever worshipped the sun, charted its movements, or built instruments to study it, from ancient astronomers tracking sunspots with the naked eye, all the way through the era of powerful ground-based telescopes and dozens of increasingly sophisticated space observatories, was working with fundamentally incomplete information, staring at roughly 2/3 of a sphere, while an entire hidden region sat just out of view the whole time. It took a spacecraft willing to spend years and multiple planetary flybys deliberately fighting its way out of that comfortable, efficient orbital plane to finally close that gap. And the very first results already revealed something genuinely unexpected, a magnetic field far messier and more chaotic than the simple, orderly picture textbooks had long assumed. Scientists are now positioned to watch, in real time and from a genuinely new angle, exactly how that chaotic tangle gradually resolves itself into two clean, orderly poles over the next several years, as this current solar cycle winds down toward its next minimum, something no human being has ever been able to directly observe from start to finish before. That transition matters far beyond pure scientific curiosity, because a deeper understanding of exactly how and why the sun's magnetic field builds, weakens, and eventually flips is directly tied to scientists' ability to forecast solar maximum with real precision, to give earlier and more reliable warnings before a dangerous storm reaches Earth, and ultimately to protect the satellites, power grids, and communication networks that increasingly define modern life. For the first time in recorded history, we finally know, with real photographic evidence rather than inference and educated guesswork, exactly what exists above our own star. And mission scientists are already promising that what we've seen so far is genuinely just the beginning of what that new vantage point is about to reveal. If this video helped you understand something you'd never really thought about before, that we've genuinely never seen our own sun's poles until this year, hit like, subscribe, and turn on notifications, because Solar Orbiter's next flyby and the sharper images that come with it are still on the way. Here's something worth sitting with. If it took 60 years in a specially engineered spacecraft just to finally see the poles of the star we orbit every single day, the star whose light reaches us in about 8 minutes, and whose activity directly shapes our power grids, our satellites, and even our auroras, what does that tell you about how much of the rest of the universe, sitting far beyond our own solar system, light years and even galaxies away, we still haven't even come close to properly seeing yet? Let me know what you think down in the comments below, and let me know whether you'd want a follow-up video once Solar Orbiter's North Pole data and its next Venus flyby results are fully released.